I'm Erin Cordes, and this is checking in on the ventilation control system. If the ventilation system is the unseen employee in a swine operation, the controller is the brains of the operation, making decisions on how all the other components of the system should react. The controller still needs a supervisor, though, providing guidance on how the controller should react to certain situations. We are going to quickly review key settings in a controller, how the controller uses these settings to react to changes in and around a room full of pigs, and how to check in on the ventilation control system. While some more sophisticated controllers may use a variety of measurements to make decisions, temperature is the primary measurement that influences ventilation control settings. The ventilation control system is a computer and uses a temperature probe to sense what is happening in the room environment. The controller then makes decisions based on the probe temperature with respect to a set point. Regardless of controller type, set point is the term we use to describe the target room condition, but it does not necessarily mean the room temperature. Most modern controllers allow you to set a set point, and the rest of these settings adjust around it. So while the set point is an actual temperature, three key settings that we're going to focus on in this video are typically temperature ranges with respect to the set point. After a quick review of these terms, we will go through some simulations to show how these settings can work together to influence room temperature and save energy. In basic terms, we need a minimum amount of ventilation in cold weather for moisture and gas removal. As the temperature increases, we need more airflow for heat removal. To provide this airflow delivery, we add additional fan capacity called stages above the set point. Below the set point, we need to provide heat to compensate for heat removed by the minimum ventilation stage. In this basic ventilation scheme for a simple ventilation system, imagine a variable speed fan that provides minimum ventilation when operating at 50% and stage 1 capacity at 100%. Two single speed fans provide stage 2 and 3 airflow needs and a heater. Let's quickly review how differential, bandwidth, and heater offset settings work. First, let's talk about the differential, sometimes referred to as an interstage differential. As temperature increases above the set point and overcomes a stage differential, the stage will turn on. It takes time for large volumes of air, like the air in a barn, to adjust. So even after the fan stage turns on, the room temperature may exceed the set point plus that differential for a short period of time. Once the temperature is on the downturn, the fan does not turn off immediately. Rather, the controller waits until the room temperature passes the differential on the other side of the set point. This reduces the number of times a fan turns on and off as the room temperature hovers around a room condition. On some controllers, the on and off differentials can be different. Bandwidth is a term that applies to variable speed fans or other components with variable settings. Bandwidth is the temperature range for a variable speed fan to go from minimum to full capacity. Variable speed fans are often used for first stage fans when only small additional amounts of airflow are needed at a time. The variable speed operation smooths that addition and removal of fan capacity, lessening the variability in the room conditions. Heaters are needed when the air we're moving for moisture and gas removal is removing too much heat from the room, causing the room temperature to drop. A heater offset establishes a new basis for heating differentials, that on-off operation of heaters. In this example, the heater activates when the temperature drops below the set point, minus the offset, minus the differential. Again, there is often some lag in the room conditions, but the room temperature eventually reacts to the heater and starts to climb. After the room temperature increases above the set point, minus that offset, the heater turns off and will not turn back on again until the temperature once again drops below the differential. You notice some overshoot in this example figure. Heating often continues after the heater has turned off. The amount of overshoot depends on many things, including the size of our heaters, but is something we need to keep in mind, and we're going to show some implications shortly. These settings, in conjunction with the set point, need to work together under changing conditions. We know seasons change and pigs grow, but even within the course of a day, there can be dramatic temperature swings. I'm going to step through some simulations with different controller settings focusing in on those low temperature conditions when a room may be transitioning between the need for heat and the need for increasing ventilation. For this simulation, we have a controller that's set to a target temperature or a set point of 70 degrees Fahrenheit. The heater offset is 0 degrees below set point, or at the same as our set point, and the heater differential is 1 degree. Minimum ventilation is provided by a variable speed fan running at 50%. As the temperature increases above the set point, the variable speed fan will increase from 50% to 100% over a bandwidth of 2 degrees. And stage 2 would turn on 1.5 degrees Fahrenheit after stage 1 is already running. When we start the simulation, the ambient temperature outside the barn is 32 degrees Fahrenheit, but starting to increase. An increase will increase over the course of the simulation. The room temperature is currently 70 degrees at or around our set point. So we're going to watch what happens to the temperature in the room relative to our different settings, as well as the ventilation and heater operation. As the simulation starts, the room temperature drops, and when it drops below the heater offset and differential, the heater turned on. It only turned on for a short time though, to raise that room temperature 1 degree, but the room temperature kept rising above the set point. So our variable speed fan was triggered to increase above its minimum setting. Meanwhile, the ambient temperature has increased to 34 and will continue to increase. As time passes, the heater, variable speed fan operation, and room temperature pattern repeats, but the pattern becomes more spaced out as the ambient temperature also increases. And eventually the ambient temperature is high enough that we are operating at stage 1 capacity. The room temperature continues to rise though, because even stage 1 is not enough to compensate for the ambient temperature conditions of 70 degrees Fahrenheit. What you notice in this simulation is that we have the heater and variable speed fans trying to compensate for one another. This is largely a result of that overshoot we talked about, both by the heating system, but also to an extent by the ventilation system. We do not have any buffer space in our settings to use this overshoot to our advantage. What happens if we make one small adjustment on our controller? Let's repeat the simulation, but first change our set point to 1 degree below set point. Let's repeat the simulation, but first change our heater offset to 1 degree below the set point, again with a heater differential of 1 degree below that. All of the fan settings should remain the same, as well as our starting ambient and room temperatures. So as our simulation starts, our heater is off, but the heater will turn on when the room temperature drops below the heater offset and differential. The heater only needs to operate for a short period of time to raise the room temperature 1 degree and then turns off. Again, the room temperature continues to climb before stabilizing and starting to drop down. As time passes and ambient temperature conditions increase, the initial pattern repeats and the time between heater operation lengthens because it is no longer needed because of the ambient conditions. The variable speed fan starts to increase more and more, going from minimum to maximum capacity as the ambient temperature increases to 70 degrees. So we only had a 1 degree difference in one of our settings, in our heater offset setting. What are the implications? Well, decreasing that heating offset in the simulation dropped the average room temperature over the length of that simulation a little over 0.5 degree. The heaters turned on 7 times with a 0 degree offset and 5 times with a 1 degree offset. The fans ran above minimum speed 66% of the time in the first scenario and 27% of the time in the second scenario. By changing the heating offset a small amount, we compensated for the overshoot by the heaters, letting that the room temperature stay below the set point, so the variable speed fan did not need to run above minimum speed. Even with that, we had little to no effect on the average room temperature. These scenarios and the settings behind the scenarios are simply an example. Each barn has its unique behavior based on heating capacity, based on ventilation capacity, and based on the room environment as a whole. But this goes to show that paying attention to the settings and watching how the barn reacts has some important implications for our ventilation system runtime and energy use. The ventilation system may be an unseen employee in a swine operation, but the controller still needs a supervisor, providing review and guidance on how the controller should react to certain situations. There are things the controller cannot sense or make sense of with its temperature probe alone. So regularly check in on a ventilation control system, keeping in mind how the differential, bandwidth, and offset settings work around the controller set point, but also with each other. These settings make a difference in how quickly the ventilation system components react to changes in the barn and surrounding environment, and how much heat and electrical energy we use in the process.